All right, we're on to Chapter 3, Section 3, and we'll be looking at formula weights. The formula weight is simply the sum of all the atomic weights of the atoms in a chemical formula. Just as a reminder, the atomic weight is on the periodic table. So here I've got the periodic table, and we'll just look at carbon because we're going to be doing carbon dioxide here in just a second. Carbon has an atomic number of 6, so the whole number is the atomic number. Of course, that atomic number tells us the number of protons in the nucleus. You guys remember that. The chemical symbol, of course, is unique. Every chemical symbol has its own atomic number, and every atomic number has its own chemical symbol, chemical element. And then the number that is not a whole number, typically, is going to be the average atomic mass. And the average atomic mass for carbon is 12.011. Now, I will note that that is the average atomic mass on Earth. If you were to go somewhere else, like Mars, it may be slightly different. That's perfectly normal. However, since we do the vast majority of our calculations for Earth, then we're perfectly fine using these numbers. So that's the numbers that we're going to be looking at when we are calculating average masses of these compounds. So we'll start by looking at carbon dioxide. Carbon dioxide, of course, is CO2. When we look at our periodic table, again, there's carbon at 12.011. Now, there's the question of how many numbers do I really need to write down? And the answer is it depends. It depends on how much precision do you need in your calculation. For example, if you only need 2 or 3 significant figures, you could round it to the whole number, 12, or 12.0. Typically, when I'm doing the calculations, I will round it to the hundredths place, which usually takes care of all of the precision we will need for the vast majority of our calculations. The reason I include at least the tenths place, and I always include the hundredths place when I'm doing these, the reason that I do that is that there are some elements where it's not really close to a whole number. And I'm just going to show you one real quick where it's not very close to a whole number. Magnesium. Magnesium is 24.305 or about 24.31. And you'll see that it's a little bit more than 1% away from the whole number of 24. A similar one is chlorine at 35.45. That's more than 1% away from the whole number of 35. So I usually discourage students from rounding to the nearest whole number unless they are doing a really rough calculation. So just keep that in mind. So I'm going to go out to the hundredths place. And since we have 1 carbon in carbon dioxide, we will do 1 times 12.01, and that will give us 12.01. For oxygen, again, I'm going to go to the hundredths place. Since this is 15.9994, we'll round that to 16.00. So we'll have 2 times 16.00. That gives us 32.00. Now we'll simply add these two numbers together, and we'll get 44.01 AMU. That number, 44.01, is the average mass of a carbon dioxide molecule on Earth. However, I will point this out. There are no molecules of carbon dioxide on Earth that weigh exactly 44.01. Most of them weigh very close to 44, and about 1% of them weigh about 45. And when you average it out, it comes out to 44.01. So keep that in mind, that these are average masses, not the exact mass of the molecule. That said, for the vast majority of our calculations, that 44.01 is going to be exactly what we want. In some situations, again, 44 is good enough. But in other situations, we'll want that extra precision. So typically, I recommend going to the hundredths place. Let's look at another one. This is for ethane, C2H6. 2 carbons and 6 hydrogens. Well, so for carbon, 12.01 times 2 gives us 24.02. And for hydrogen, you could go out to 1.01 or 1.008. There's an argument to be made for both of those. I'm just going to go to the hundredths place to make it easy. So 6 times 1.01 gives us 6.06. We'll add those together, and of course we get 30.08 atomic mass units. Now, we're going to practice doing this a lot, so you will get plenty of practice multiplying all of these things out. So you need to become not just good at it, you need to become essentially perfect at it, because this is the basis for doing many of our calculations this semester and in general chemistry too. So calculating percent composition. The percent by mass of an element in a compound is given by this formula. So the percent of that element by mass is going to be the number of atoms of that element in our formula times the atomic weight of that element divided by the formula weight of the compound, and then we multiply by 100 to make it a percentage. For the compound C2H6, we will find that there's 2 carbons. So if we want to find the percent carbon, we'll put 2 for carbon. The atomic weight of carbon is 12.01. And the formula weight of C2H6, as we saw on the previous page, is 30.08. Multiply by 100, and we get 79.85%. And that is out to 4 significant figures. All right, so let's look at number 24 on the in-class assignment. So it says, calculate the percent by mass of nitrogen in ammonium sulfate. Well, the first thing that we're going to need to do is we'll need to get the formula weight of ammonium sulfate. So we need to count how many of each element. There are 2 of the nitrogens. So nitrogen, and I'll pull over the periodic table here. Nitrogen is 14.007. Again, I'm going to round that to the hundredths place, so 14.01. So 2 times 14.01. For hydrogen, we've got 4 times 2, so that's 8. 8 times 1.01. We saw that a minute ago. Sulfur, we saw that. I don't think we've seen that one here. There's 32.066. We're going to make that 32.07. So 1 times 32.07. And then for oxygen, we've got 4 of those. So 4 times 16.00. And we're going to add all of those together. And clearly I didn't leave enough space to add these all up. So I'm just going to write the whole number over here. Let's see. So this is 28.02. That one's 8.08. This one, no calculator needed, 32.07. And then 4 times 16 comes out to 64.00. So now we will add all of those together. Get my handy dandy calculator here. Looks like I was doing some trigonometry earlier. Clear that. So 28.02 plus 8.08 plus 32.07, 64. And we get a formula weight that is equal to 132.17 AMU. All right, and now we want to get the percent nitrogen. So to get the percent nitrogen, we'll do the number of nitrogen atoms, which is 2, the mass of nitrogen, which is 14.01, divide by 132.17, and then multiply by 100. So 2 times 14.01 equals that, 28.02. We'll divide by 132.17. All right, and then we're going to multiply that by 100 to make it a percentage. And we've got 4 significant figures, so we're going to call that 21.20% nitrogen. So that means that 21.20% of this substance is nitrogen by mass. All right. So let's look at another one. Calculate the percent mass by water in calcium sulfate dihydrate, and that's CaSO4 2H2O. All right. So we'll need to get each of these elements. So for calcium, we've got one of those. So 1, and calcium is 40.08. All right. Sulfur, we've got one of those. So 32.07. We had that one a second ago. Oxygen, so there's 4, and then this, I purposely picked this hydrate because the way this molecule works is that this is an ionic compound, calcium sulfate, and for every unit of calcium sulfate, there are 2 water molecules that are trapped in that crystal. And so that means we have 2 H2O molecules in there. So we kind of multiply this out. So we'll have 4 plus 2 more. That gives us 6. 6 times 16.00. And then for the hydrogen, we've got 2 times 2, so that's 4. 4 times 1.01. All right, so that's 40.08, 32.07. And then here we've got 6 times 16, that's 96.00, and then 4.04. All right, so we'll do 40.08 plus 32.07 plus 96 plus 4.04. And we get a formula weight that is equal to 172.19 AMU. Now, since this is asking for the percent by mass of water, well, then we want to do this this formula. Our percent H2O in a hydrate like this. All right. So the percent H2O is going to be the number of H2O molecules times the formula weight of H2O divided by the formula weight of our hydrate. And then times 100 to make that a percentage. So for this particular calculation, our percent H2O is going to be 2. And then our formula weight for water, it's 2 times 1.01. Oh, I should probably write this. I'm going to write this over here on the back real quick. So for H2O, so 2 times 1.01, which of course comes out to 2.02. And for oxygen, 1 times 16.00 comes out to 16.00. And that gives us 18.02 AMU. All right. And I do that calculation just so you know, and I'm not going to do that one again because you now know it. So 18.02, and then we'll divide by the 172.19 that we had a little bit earlier, and then we multiply that by 100%. So now we'll get our handy-dandy calculator out. So 2 times 18.02 divided by 172.19. Multiply that by 100, and we get 20.93% H2O. All right. So that is calculating percent of an element and also calculating percent water in a hydrate. And that is a useful calculation to be able to do. All right. So now what we want to do is we want to move on to the mole. So the mole and Avogadro's number. So the mole is a way of measuring something on a laboratory scale when previously we were talking about on the atomic scale. So it used to be that the definition was a little bit different, but in 2019, in May of 2019, the mole was officially redefined as exactly 6.022140076 times 10 to the 23rd constituent particles. And that could be atoms, that can be molecules, that can be ions, it can be electrons, it can be anything, but we're going to talk about atoms and ionic compounds and molecules here first. So that is the definition. The old definition was exactly 12 grams of carbon 12, but it turns out that definition is not used anymore. So we are now onto this definition. The good news is that the numbers don't really change because we have so many significant figures here. We've got 9 significant figures in there. Well, this is an exact number, but in terms of converting between AMUs and moles, it's almost exact. So we're good there. We refer to this as Avogadro's number. Avogadro's number is an extremely useful number. We'll often just round that to 6.022, but those other numbers, if we need more sig figs, there they are. Here is the number all written out. So 602,214. I'm not going to read all that out. 602.2 sextillion units. It's a lot of particles. It is a lot of particles. So if we look at the picture over here on the right, that picture shows what 1 mole of several different substances looks like. And what it looks like is going to be it's going to be different depending on what the average mass is of the atoms, and also depending on its density. The density will make it look bigger or smaller. So here is an American quarter for scale, and then here we've got 12 grams of carbon graphite that's been pressed into a cube at 12.01 grams. So there we go, 12.01 grams, and you'll see that is 6.022 times 10 to the 23rd carbon atoms are present in there. For copper, you'll see that it's bigger and it's heavier, and so 63.55 grams for purposes of like what that would be for standard American units. That's a little bit over 2 ounces of copper. So a little bit over 2 ounces of copper. Here we've got aluminum, 26.98 grams. You'll see that it's bigger, but it actually weighs less than the copper, and that's because aluminum is a lot less dense than copper. So what it looks like is going to be different, but the thing that all of these have in common is that they all have 6.022 times 10 to the 23rd atoms. All right. Now, we can do Avogadro's number of anything. We can do it for molecules. 1 mole of water molecules is going to come out to 6.022 times 10 to the 23rd water molecules. Again, the whole point of Avogadro's number is that it takes us from the atomic mass scale to the gram scale, the laboratory scale. And so 1 molecule of water weighs about 18.0 atomic mass units, whereas 1 mole of water, which is 6.022 times 10 to the 23rd water molecules, is going to weigh about 18 grams. All right, 18.02 if we want to go out to another sig fig, as we saw a minute ago. All right. Typically, when I do this in class, I have a whole bunch of samples that I like to pass around and show my students. And so, like, I've got water and I've got carbon. I'm going to show you a picture of what these look like. Here we go. So here's water. That's 1 mole of water, comes out to 18 grams. There's 6.022 times 10 to the 23rd water molecules there. Here I've got carbon. There's 12 grams of carbon. So 6.022 times 10 to the 23rd carbon atoms. Here I've got some silicon. All right, you'll see it says 28.0855 grams. And that is 1 mole. So there are 6.022 times 10 to the 23rd atoms of silicon in there. Here's copper. Copper, I believe, let's see. I've got my periodic table here. It comes out to 63.55 grams. There is zinc. Zinc comes out to 65.38 grams. There's sodium chloride, so you can do this for an ionic compound. And I don't know the exact mass of it, but it comes out to, it's about 58 or 59 grams. I forget the exact number. But that is 1 mole of copper. And then here we've got 1 mole of sucrose, and sucrose is C12H22O11. It's a huge molecule compared to all this other stuff, but that's 1 mole of sucrose, and it comes out to about 342 grams. The reason I do this is to point out that 1 mole looks a lot different depending on what substance you're talking about. There are just as many water molecules in this container, the water container over here on the left, as there are sugar molecules in this container. And so, again, what 1 mole looks like really depends on what substance you are talking about. So these are all the substances we just went through. So carbon, copper, zinc, silicon, sodium chloride, and sucrose. Okay, so that's what Avogadro's number of particles looks like. Again, it just depends on which substance you are looking at. So now we want to calculate the molar mass of different substances. And the molar mass of 1 mole of a substance, so the molar mass of 1 mole of a substance is going to be the mass of 1 mole. So yeah, the molar mass is the mass of 1 mole. So the molar mass of an element is simply the atomic mass, but in grams per mole. So for example, the average atomic mass for copper, again, I'm looking at my periodic table here, for copper comes out to 63.546. All right, so about 63.55 if we just want to round to the hundredths place. Well, that is how the average mass in AMUs for 1 copper atom. But if we want 1 mole, 6.022 times 10 to the 23rd copper atoms, it's going to weigh 63.55 grams. That's what the molar mass does for us. The molar mass of a compound is simply the formula weight of that compound, but again, written in grams per mole. So let's do carbon dioxide. We did carbon dioxide for formula weight a little bit ago. Here we're going to do it for molar mass. 1 times 12.01, 2 times 16.00. We add those together. We get 44.01. Perhaps this looks familiar. This is the exact same calculation that we did earlier. The only thing that's different is previously when we did formula weight, it was in AMUs. And now it is in grams per mole. That's the difference. Let's do another one here. This is the molar mass. Oh, hey, we just did this one, but we did it as formula weight a minute ago. Calcium sulfate dihydrate. All right, so that is the mineral known as gypsum. So calcium sulfate dihydrate. So 1 calcium atom at 40.08. Sulfur, 32.07. So we had 1 of those. For oxygen, we had 6 of those. So 6 times 16.00. And then finally for hydrogen, We had 4 of those, so 4 times 1.01, and that gives us 4.04. We added all those together. That's exactly the same number that we had a minute ago when we did number 33.24, and that it was that second part of 3.24. All right, so that is that one. Let's do another one, and then we will do some calculations on the in-class assignment. So now we want to calculate the molar mass of calcium phosphate. I picked this one on purpose because of the parentheses, and I want to make sure that everybody gets what it is we're doing here. So again, calcium, we've got 3 of those calciums, so 3 times 40.08 comes out to 120.24 grams per mole. For phosphorus, we've got 2 phosphorus atoms, so the parentheses, the 2 here outside the parentheses means we need to multiply each of these by that 2. So 2 times 30.97. For oxygen, it's 2 times 4, so we have 8 of those, so 8 times 16.00. And when we add all of those together, we get 310.18. All right, so let's look at number 29 on the in-class assignment. Here we are, number 29 in class. Clear out that last calculation. All right, so I would pause the video at this point, attempt to do these on your own. Again, go out to the hundredths place, and then just watch the video, and you'll be able to follow along. All right, so here we've got carbon. There's 6 of them, so 6 times 12.01. So 6 times 12. 72.06. All right, for hydrogen, we've got 12 times 1.01, 12.12. And then for oxygen, 6 times 16.00, and that comes out to 96.00. We'll add those together. So plus 12.12, plus 96. And that gives us 180.18 grams per mole. All right, so this is pretty easy to do. All right, for magnesium, all right, I showed you, I don't know if I showed you magnesium earlier. Here's magnesium, 24.305. We're just going to call it 24.31. So 3 times 24.1. So all right, for phosphorus, we have 2 of them. So 2. And phosphorus is 30.97. Let me 0.97. So 2. So 61.94. And just so you see where I'm getting that 30.97 for phosphorus. All right, oxygen, we have 8 of those times 16.00. And 8 times 16 comes out to 128. So 128.00. All right, so that plus, and I'm just going to go up and grab these numbers, plus, all right, and we get 262.87 grams per mole. All right, I was just double checking my math to make sure I didn't make a mistake there. All right, so next we'll do ammonium carbonate. So nitrogen, well, nitrogen, I don't know if you saw this earlier, nitrogen, is 14.007. We're going to call it 14.01. So we'll have 2 times 14.01, 28.02. Hydrogen, we've got 8 of those, 4 times 2. So 8 times 1.01, 8.08. Carbon, we've got 1 of those times 12.01. It's 12.01. And then finally, oxygen, we've got 3 of those. So 3 times 16.00, and that comes out to 48.00. So now we just need to add those numbers together. So 28.02 plus 8.08, 12.01 plus 48.00. And we get 96.11 grams per mole. Okay. Here we go. All right. So now that we've done that, we have practiced doing calculating molar masses. We're going to go back to our in-class assignment here, or not our in-class, but our presentation. And we want to look at how we convert from mass to moles and from moles to mass. So from mass to moles and moles to mass. We're going to start by doing from mass to moles. Up here at the top, I've got a little bit of what I'm later going to call the roadmap, but it's just a way of solving problems. Whenever you convert from mass to moles, you use the molar mass. Whenever you convert from moles to mass, you also use the molar mass. It's just one way you divide and the other way you multiply, but you're going to use that. You're going to be using that as your conversion factor between the two. So if we have a problem like this, says how many moles of carbon dioxide are in 1.34 grams of carbon dioxide? Well, here we're going from mass to moles, so we'll use the molar mass. In this case, if we follow the dimensional analysis, the molar mass of carbon dioxide came out to 44.01 grams per mole. So I'm going to divide by the molar mass, and you'll see, since it's 44.01 grams per mole, our moles will end up in the numerator. Our grams will be down here in the denominator. Doing dimensional analysis, we can cancel out the grams of CO2, and now we just divide 1.34 divided by 44.01. We've got 3 sig figs, so our answer is going to come out to 0.0304 moles of CO2. We can, in a very similar fashion, do the same calculation, but going the other way, from moles to mass. So, for example, if we want to know how many grams of CO2 are in 2.06 moles of CO2, well, we'll start with the number that we know, the 2.06 moles of CO2. Instead of dividing by the molar mass, though, we're going to multiply by the molar mass. You don't have to memorize, oh, it's divide going this way and multiplying going the other way. The best way to do it is just to do the dimensional analysis. So our molar mass is 44.01 grams per mole. Our moles of CO2 will end up canceling out. And we'll just take those numbers and multiply them, and we have 3 sig figs. So we'll go out to 90.7 grams of CO2. So let's look at number 30 on the in-class assignment. So here is number 30. We'll clear all that stuff we did a minute ago. So here we want to know the number of moles of glucose, C6H12O6, in 27.1 grams of this substance. All right, that's easy enough. So we have the mass at 27.1 grams. And one thing I'm going to do is I am going to write out the units. So grams of C6H12O6. It may not seem important here, but it will become important later when we're doing stoichiometry calculations. So, all right, when we're going from grams to moles, we're going to divide. And again, you can remember that based on the dimensional analysis. Now, I purposely picked these substances because they're the substances that are here. And so I'll do 180.18 grams of C6H12O6 per mole of C6H12O6. All right, so 27.1. All right, and we've got 3 sig figs, so that 0.1504, we are going to round that to 0.150 moles of C6H12O6. And if you want, if you're feeling up for it, of course, you can do the dimensional analysis and cancel out the grams of C6H12O6. Now, again, I encourage you to write all these units out when you're doing this. You're less likely to make mistakes if you write down all of your units. Okay. Next, let's look at magnesium phosphate. So we've got this many moles, so 906 rather. 1.906 times 10 to the negative 2 moles Mg3 PO4 2. Here we're going to end up multiplying by the molar mass. Our molar mass, as we determined in that previous problem, is 262.87. So 262.87 grams of Mg3 PO4 2 per mole of Mg3 PO4 2. All right, we'll do a little bit of dimensional analysis. Our moles of magnesium phosphate cancels out, and we'll now just multiply that out. So 1.906 times 10 to the negative 2 times 262.87. And 4 sig figs, so we're going to write that down as 5.010 grams of Mg3 PO4 2. All right, next, let's look at ammonium carbonate. For ammonium carbonate, here is ammonium carbonate. So now we've got the number of moles, and we want to get the grams. So 2.50 times 10 to the negative 3 moles of NH4-2CO3. All right, our molar mass of ammonium carbonate was here at 96.11, and since that's grams per mole, our grams are going to go up in the numerator, so 96.11 grams of NH4-2CO3 per mole of NH4-2CO3. I'll go ahead and do dimensional analysis here. Our moles of ammonium carbonate cancels out, and now we'll multiply all of that. So 2.50 times 10 to the negative 3, 96.11. And we've got 3 sig figs, so we will write 0.240 grams of NH4-2CO3. Okay, so now that we've done those calculations, we want to go back to our presentation here, and we want to look at converting to formula units. So converting to formula units. And this is, it's an important concept, so that's why I include it here. And so here we're going to convert into the formula units. We already know how to get from mass to moles and moles to mass. Divide one way, multiply the other. But if we want to get from the moles to the formula units, then we can do an extra calculation. Or if we want to get from mass to the formula units, we can just put it all in one line and do one big calculation. And so here's a question we might want to answer. How many molecules of carbon dioxide are in 278 grams of carbon dioxide? Well, we'll start with our mass. And every time we go from one box to another, we'll use whatever is in the middle as our conversion factor. So 278 grams, we will multiply or divide that by the molar mass of carbon dioxide. The molar mass of carbon dioxide we saw a little bit earlier was 44.01. So we divide that. Now we have moles. Well, to get from moles to the number of formula units, that's easy enough. We'll just multiply by Avogadro's number. Well, Avogadro's number, 6.022 times 10 to the 23rd molecules of CO2 per mole of CO2. Again, I'll do the dimensional analysis, and then our number of molecules just comes out when we do the calculation. All right, so easy enough. And we're gonna do a problem number 31. And we actually take that a step further when we do 31 here. All right, get all of that on screen. So how many molecules of C6H12O6 are in 3.44 grams of this substance? All right, so 3.44 grams of C6H12O6. All right, our molar mass is from that previous page is 180.18. It's right there. So 180.18 grams of C6H12O6 per mole of C6H12O6. Okay, and now we want to get to the number of molecules. And here we'll go ahead and do our dimensional analysis. Our grams cancel out. So to get to the number of molecules, we just have 6.022 times 10 to the 23rd molecules of C6H12O6 per mole of C6H12O6. All right, and moles will cancel out. So dimensional analysis definitely can be your friend here. All right, we'll clear all that. We have 3.44 divided by 180.18. Go ahead and hit enter, and now I'm just going to multiply by 6.022 times 10 to the 23rd. And that gives us, and we have 3 sig figs there, that gives us 1.15 times 10 to the 22 molecules of C6H12O6. All right, next on this one, we've got an extra calculation that we need to do, and that's why I picked this one, because I think it's kind of interesting. All right, so 183 grams of Mg3PO42. We're going to convert to moles of magnesium phosphate. And our molar mass of magnesium phosphate, again, that was on that previous page, 262.87 is right there. So 262.87 grams of magnesium phosphate per mole of magnesium phosphate. All right. Now, I'm going to do one additional calculation before I convert to the atoms, and that is in every mole of magnesium phosphate, how many moles of magnesium are there? And if you look, that subscript will tell us the answer. We've got 3 moles of magnesium atoms per 1 mole of magnesium phosphate. All right. And so far here, we can do this dimensional analysis. So grams of magnesium phosphate cancels out. Moles of magnesium phosphate cancels out. And now we're going to do, there are 6.022 times 10 to the 23rd magnesium atoms per mole of magnesium. And I didn't leave a lot of space here, but we'll see here that the moles of magnesium cancels out. So we'll clear all that and we'll do 183 divided by 262.87. And then I'm just going to hit enter, and then we'll not divide, multiply by 3. And then we'll also multiply by 6.022 times 10 to the 23rd. And the number we get there, we've got 3 sig figs, so we're going to call that 1.26. So I'm going to write it right here, 1.26 times 10 to the 24 magnesium atoms. All right, so now we have done that particular calculation. There's one more thing I want to do before we end this video, and that is looking at mole relations. So there's going to be times when we're interested in how many moles of an element do we have versus how many moles of the elemental molecular substance do we have. And so I'll mention this as we move forward. I'll show you different examples of this. But like in the next thing that we're going to be doing, we're going to be looking at like how many moles of the atomic element do we have. Whereas there are going to be other times where we're interested in the molecular. So you just have to pay attention to the context. Of course, this molecular nitrogen is going to be twice as heavy, so twice as big as the atomic nitrogen would be. Another thing I like to point out is, so here we've got silver and silver ion, and we can do moles of either of these, but you'll notice that the formula weight comes out essentially the same, and that's because the mass of the one electron is so small that it would show up not in the 9, not in the 10th place, not in the 100th place, not even in the 1000th place, but in the 10,000th places where you would really start to see that number show up. So it's so small that it's not really a concern. It's often well outside the margin of error in your measurements. In addition to that, if you've got sodium ion here that's positively charged, something else is going to have the negative charge. Something's going to have wherever that missing electron is, something else is going to have that. And then the other thing is that you can measure this for ionic compounds. You can measure it for any kind of compound. It can be any particles, really. And so that is what we mean by the Avogadro's number. And in fact, 1 mole of molecules or formula units contains Avogadro's number times the number of atoms or ions in each element of that compound. So, all right, well, that is the end of this section, and I'll make, or at the end of this video, and so I will start the next video, and we'll be talking about calculating empirical formulas.